In 2019, the global metrology community agreed on a redefinition of the kilogram. They retired the physical block of metals stored in France and anchored mass to Planck's constant. Planck's constant is the exact numerical value that dictates the minimum energy of a quantum electromagnetic wave. Physics classrooms teach a strict assumption. The kilogram is an independent base dimension. It measures mechanical mass completely separate from electrical current or luminous intensity. But an equation is only as reliable as its units. If the unit measuring mass contains an unacknowledged variable, every calculation that relies on that mass will drift off target. The major anomalies in modern physics, the extreme weakness of gravity, and the accelerating expansion of the universe, trace back to this specific oversight. They are mathematical artifacts created by a broken ruler. On the microscopic scale, physicists face the hierarchy problem. Gravity is incredibly weak, about 36 orders of magnitude weaker than electromagnetism, and the Standard Model offers no mechanical explanation for this discrepancy. On the macroscopic scale, the James Webb Space Telescope is detecting massive, highly structured spiral galaxies at extreme redshifts. According to the standard timeline of the universe, these galaxies are too young to possess this level of maturity. These specific anomalies share a mechanical root cause. Our calculations separate mass from electromagnetism in the lab, and they assume light propagates through a completely empty vacuum in space. The triphase framework demonstrates that the kilogram is an electromagnetic artifact. By factoring vacuum impedance into our equations, the requirement for dark energy and entirely new branches of physics disappears. We can derive the exact numerical value for the gravitational constant, or G, using only the permittivity and permeability of the vacuum. Vacuum permittivity and permeability are the measurable electrical resistance and magnetic capacity of empty space. The numerical output matches the measured value of G to within 0.5%. However, the units fail to close. The dimensional analysis leaves an ampere squared term in the numerator. Standard academic convention rejects this derivation. The rulebook dictates that electrical current cannot exist in an equation describing mechanical gravity. Yet the modern Kibble Balance, the exact instrument now used to define the kilogram, determines mass by measuring the electromagnetic force required to counteract gravity. The measurement system itself relies on electrical current to define weight. Albert Einstein established that energy and mass are equivalent, with E equals mc squared. Max Planck established that energy and frequency are equivalent, with E equals h bar omega. Setting those equations equal to each other establishes that mass and frequency are identical properties. The kilogram is a label for a highly specific threshold. It represents the energy accumulated when a wave packet reaches a steady-state frequency of 8.52 times 10 to the 50th radians per second. Space possesses an immense electromagnetic rigidity. Gravity is the minute residual force remaining after the magnetic cancellation within this frame. We perceive gravity as weak only because we measure it against a historical unit that hides its own electromagnetic frequency. This unit mismatch directly impacts astrophysics. Whether measuring parallax, triangulating eclipsing binaries, or tracking standard candles, every cosmological distance calculation relies entirely on the measurement of light. The Standard Model calculates these distances using a lineal ruler. It assumes light travels in a perfectly straight path at a constant velocity indefinitely, multiplying the speed of light by the redshift, which is the observed stretching of light wavelengths, divided by the Hubble constant. Space is not an empty void. It has measurable impedance. As a wave packet travels across billions of light years, it interacts with this resistance.
The packet loses energy, its wavelength stretches, and its group velocity drops. Accounting for this physical resistance requires replacing the linear formula with a logarithmic one. Distance equals the speed of light divided by the Hubble constant multiplied by the natural log of 1 plus c. This chart shows wavelength-based and geometric distances calculated with the logarithmic formula. The green and red curves overlap completely, demonstrating strict internal mathematical consistency. Standard cosmology calculates expansion by ignoring the physical friction of the vacuum. This omission causes the linear formula to systematically overestimate the universe's scale. This chart displays how the standard linear ruler overestimates true distance. At redshift 1, it stretches the actual distance by 52%. Deep in the early universe at redshift 10, the standard model overestimates distances by over 80%. This graph compares the divergence of geometric and wavelength distances. The tri-phase framework maintains the flat green line of absolute agreement, while the standard formula in red spirals upward. At z equals 10, they diverge by over 1,600%. We can test this divergence against actual physical measurements using the water masers in galaxy NGC 4258. Water masers are dense, microwave-emitting gas clouds orbiting a central black hole that provide extremely precise, direct geometric distance markers. This plot maps 7 megamasers' geometric distances against wavelength distances. Blue circles represent the standard linear calculation, drifting steadily upward from measurement agreement. Green squares show the logarithmic correction, clustering precisely at 0, entirely within the green band of measurement uncertainty. The physical observations from the masers confirm the mathematics. Distance decay is logarithmic. The linear expansion model contradicts the physical evidence. For decades, cosmologists have struggled with the Hubble tension. Measurements taken from nearby Cepheid stars yield an expansion rate of roughly 73, while measurements from the distant cosmic microwave background yield an expansion rate of 67. The entire tension is a math error. At close range, the linear formula slightly underestimates distance, artificially inflating the local Hubble constant. At long range, it massively overestimates distance, dropping the distant Hubble constant. Applying the natural log correction to both datasets yields a single, uniform expansion rate of 71.48 kilometers per second per megaparsec. This correction directly resolves the anomalies captured by the James Webb Space Telescope at redshift 10. Under the linear math, these galaxies appeared impossibly mature, but the linear math was overestimating their position by over a factor of 16. They are significantly closer to us than previously published. Because they are physically closer, the timeline shifts. These systems had billions of additional years to develop the complex spiral arms and mature structures we observe. Dark energy, the Hubble tension, and impossible early galaxies are all downstream effects of using a 19th century unit of mass and an uncorrected linear ruler. By treating mass as an electromagnetic frequency and calculating distance based on the logarithmic impedance of the vacuum, the observable data aligns with the mathematical derivations. These phenomena are connected by the underlying physical architecture of the vacuum, the three-phase vector frame. Space is an active, highly structured electromagnetic circuit. The wave packets of light we observe are navigating the specific physical resistance of that circuit. The standard model addresses observation gaps by injecting placeholder concepts, rapid expansion rates, dark matter, and dark energy, to force broken equations to balance. The universe is structurally consistent from the lab bench to the cosmic horizon. We simply need to stop isolating our base units and start measuring space with an honest ruler.